So yesterday, we took a step away from cluster algebras and for a moment just considered this more general setup, or like a bit of a different setup of having an ideal inside of a polynomial ring and look at its tropicalization. So this was our setup. We have I, an ideal, polynomial ring of the complex numbers or other fields. And we associated 3 fans to this idea. The first one was the Gröbner fan. Living in this space R to the capital N, the number of variables inside the positive orthant, and being full dimensional, and points in this fan classified as different initial ideals we could get from this ideal. So it was full dimensional. And then inside of here, we had the tropicalization. As kind of a non-generacy locus in here, where we were only considering initial ideals that did not contain any monomials. Right, so here we had maximal cones corresponding to monomial ideals. And here we're still sitting in the same space, but the dimension now is the dimension of the affine variety associated to the ideal. And maximal cones correspond to, at most, binomial ideal. And then in the case when my ideal is defined over the real numbers, I had one more fan that I could associate, and that is the positive part. Of the tropicalization. The dimension now depends on the ideal. This was only defined if my ideal itself is totally positive, or is totally positive in the sense that it does not contain any non-zero elements, polynomials with only positive coefficients. Yeah, I think the rest is fine. So here I cannot make any more general statement about dimension. Okay, so I want to get back to cluster algebras. So our setup from now on will be a cluster algebra of finite type. So in particular, we have a finite set of cluster variables. And this allows me to define a map from the polynomial ring in as many variables as I have cluster variables. Maybe I put tildes here. So these are just abstract variables. Let's call this map phi. And then A is isomorphic to the quotient of the polynomial ring by the kernel of phi. So this is what I would call a presentation of this algebra. Great. So in this setting, well, for the cluster algebra, we can also go again to the geometric side and consider the cluster variety. Let's put a Q here just to have the notation as before. Then we have AQ, the cluster variety. And what happens here on the level of algebras has an interpretation on the level of the varieties. So what I can do here is I can define an embedding, or the same kind of selection of clusters defines an embedding of the cluster variety into the vanishing set of this ideal. So this, I will call it now I. And let's get a bit of notation first. So I have an initial seed here. No, so the cluster algebra, if this is the set of all cluster variables, then the cluster algebra is the subalgebra of this field of rational functions. And here I have, yeah, but for the cluster algebra, I'm okay with just the coefficient. Okay, so now if I fix the seed for my cluster algebra, this means in this set of all cluster variables, some are the initial cluster variables, and all the others have Laurent polynomial expressions in these original cluster variables. Right, so in particular, and let's assume here that the first n plus m are my initial seed, and the rest are just the rest of the cluster variables. Are my initial cluster. So then for let's say then every x k with k greater to n plus m as an expression I will denote it by x capital K, and this lies in a Laurent polynomial ring where my generators are the initial cluster. The mutable ones, I have to also allow inverses. And for the others, the frozen ones, I can only allow polynomials. And in fact, so this statement itself is the Laurent phenomenon. And then when I adjust coefficients to be non-negative, this is the positive Laurent. So this is what we saw in the second lecture. Okay, so now I can define also a geometric map. And it will go from my cluster variety and land in the vanishing set of my ideal presenting the cluster algebra. And so a tuple of points here, if I just restrict myself for the initial seed, so remember this is the union of tori. So I will write down the map for you in one of the tori. And the transition functions will allow you to get the map in the rest of all the cluster charts. So I would say by defining it in the initial seed torus. So a point here is an element in C star to the n plus m. And my coordinates are exactly my initial cluster. So I have a tuple A1 to an plus m. This affine variety lives inside an affine space of dimension capital N, and its coordinates are all the cluster variables. Or their tilde representatives. So what I do here is I take this tuple and I send it to the point where the first n plus m coordinates just stay the same, and the others, I will take these Laurent polynomials and evaluate them in this tuple A. Right, exactly, yeah. And so when I change my seed now, I would just get a different collection of capital X's, and that gives me the way how to transition from one chart to the other. Okay. Is that clear? Any questions? Okay. Great. So in particular, we get an embedding of the cluster variety in this affine variety. And now we have two different ways of tropicalization at hand, right? We saw how the cluster variety has its own theory of Fock-Contour of tropicalization by gluing lattices according to tropical mutation maps. And we've seen how the ideal has its own tropicalization by following this Gröbner construction. Right, so it's a natural question is now, how are the tropical spaces related? And in and of itself, the question is maybe not so interesting because we can tropicalize this map, and that will be a map between the tropical spaces. But the question is more finely about how do the fan structures compare? Because both of the tropicalizations come with a lot of extra data associated to them. So here we want to understand how that data, if that transfers, if that survives this map. And maybe I'll give you the result, and then we look at this running example of the Grossmannian 2-4. And let's call this map iota S. Right, so or maybe first let's see what it means to tropicalize the map. Yeah. So let's tropicalize this map iota. On the left-hand side, we have the Fock-Contour of tropicalization. Or let's leave away the spaces. Let's just take them as a map from R to the n plus m to R to the capital N. Right, this we can certainly do. So we just take these coordinates and we tropicalize in the way that we had before, where in these polynomials or Laurent polynomials, whenever there is an addition appearing, I will replace it by taking the maximum, and multiplication will be replaced by addition. So we get un plus m The inverse? This is minus. So remember the semi-fields, there are still groups with respect to their multiplication. So we have inverses of the auxiliary addition or the auxiliary multiplication, which is usual addition. Minus signs are fine here. Yeah, just what does not have an inverse is taking the max. This here we still have a abelian. Okay, so now what's the theorem? If I take this tropical map now, it sends the fan that we've defined before, the Fock-Goncharov cluster complex, to the positive part of the tropicalization of my idea. And it's so this is not as a map of sets. This is maybe fine. This is expected, but it also preserves a lot of structure. So first of all, this is an isomorphism of fan. Meaning that a cone here is sent to a cone here. And we have a bijection between rays in the positive part of the tropicalization of the ideal with cluster variables. And we have a bijection between maximal cones in the positive part of the tropicalization and C. Okay. These are all cluster variables. Yeah, these are my. So the number of rays here is exactly the number of cluster variables. The maximal cones correspond to C, and the adjacency is preserved. So this is the cluster complex, meaning two maximal cones here. If they are adjacent seeds, and there's one mutation relating the two seeds. And so if I have a cone here, and let's just do an example. So what does this mean if we have S1 and S2 adjacent maximal cones? Oh, and one more thing is, of course, that this is also simplification. So if I have two adjacent maximal cones in the positive part of the tropicalization, then because I am simplicial, there's only one ray that is generating one of them and not the other. Or like, let's say a pair of rays are two rays such that Ri is generator of sigma I and not of sigma, the other one, J. Okay. And these two exactly correspond to cluster variables that are mutable, that are the mutation from one of these cones to the other. So the statement, let's call them 1 and 2, then the theorem also says there exist seeds S1, S2, and cluster variables, say X1 in S1, X2 in S2, and X2 is the mutation of X1. So they are related by mutation. yeah, and they correspond to the rate. And in fact, there's a way to make this explicit by considering the G vectors of these. So in this span, we have G vectors of all cluster variables. And if I take the G vector of one of those cluster variables and send it through that map, it will be mapped with the ray. So oh, right, yes. Okay, let me go over there. Yeah. So if I have sigma in R to the something, a cone, then there exists a set of one-dimensional cones, and these are called rays. And I will, or maybe I don't even need that. We just take yeah, I will just take so there exists some points in Rn such that sigma is all the integer or all the real positive combinations of these. So no. And the span of one of those VIs is called the ray. So this is a one-dimensional cone. Right? I have some points in R to the n that satisfy this condition. And if I take the positive span of just one of those, this is called a ray. Yeah, let's put minimal. Let's pick a minimal set. Yeah, thank you. Okay. Right. So yeah. Okay. So just the last statement that I said is that if I take the G vector of one of those cluster variables, this map iota, tropicalized, sends it to the ray. Yeah, I think it's a bit tough for me to define it now, but it's every cluster variable has associated to it it's a G vector, and in fact the G vectors we can think of them as the rays in this span. So let's maybe have it like that. I think they appear. Yeah, did you define them? Yeah, I think, okay, yeah. We saw them defined very briefly in Tajikistan. But yeah. Okay. Any questions about that? Or let's verify the example. Yeah, this works in general. Here, I'm not assuming anything. This could also be non-rational points in R to them. But for my application, the cones will be simplisher. So that means the number of generators, the number of rays coincides with the dimension of the cone. Yeah, let's say this is a finitely generated cone. Okay, I can also make it an integer simplistic cone, as in my example. Then these are actually lattice points, and P is the dimension of the cone. This is the generality I need. Okay. Okay, so let's go to the to the example. Of the affine cone of the Grassmannian 2,4. So this is the vanishing set of the Plücker relation. All the Plücker coordinates are cluster variables. We're in cluster type A1. So we had two seeds and the transition map obtained from the Plücker relation. We saw the tropicalization of the Plücker ideal. Has three cones, three maximal cones that correspond to dropping out one of the monomials of the relation. So I had the cone how 1, 2, would correspond to the where the cone where in the initial ideal I dropped the first term, and then I had similarly 1, 3 and 1, 4, dropping the term with 1, 3 and dropping the term with 1, 4. So for the cluster variety, we also computed the tropicalization, the Fock-Ontroff tropicalization. Or I think what we computed the cluster complex. Let's put it like that. So we have the cluster complex, sigma S, and it also has two maximal cones. Sigma S. And here I'm in a lower dimensional ambient space, right? Here I'm in a space of dimension 6. Here I'm just in a space of dimension 5, because this tuple only corresponds to one of the two clusters. Right, so my two. Right, edges here correspond to the indices of my coordinates. And then I had the condition that U12 plus U34 is greater or equal to U14 plus U23 and is also greater or equal to U13 and sigma S prime, where this is the other way around. Right, and this came from the tropicalization of the mutation formula or this exchange relation, right? So we had P4 if we tropicalize this relation, we got this, and then depending on which term wins the race of the maximum, we get two different cones. Okay, and now let's write down this map in this case. So this is here. Remember, the points in here lie in the same cone. If I take the initial ideal, if I take them as weights and I look at the initial ideal, the ideal is the same. So in the tropicalization, I don't allow initial ideals that are monomials. So I can only go to a binomial initial form. And this is the condition on W's to ensure that this will be my initial form. So if I have W in tau 1, 2, and if I actually want to ensure the initial form is the binomial, I would go to the interior of the cone, not allowing equality here. And now we can compute what happens when I take initial form with respect to W. This is equality. This is equality, so this ensures me that these two have the same weight. Yeah, and this is smaller, so this is the maximum, exactly. But here I write down the closed cone, so I allow equality as well. Okay. Okay, so the maps in this example are map iota S, and let's think of this as my initial seed S from the cluster variety to the affine cone of the Grassmannian, takes the tuple indexed by edges in this triangulation, and sends it to, we keep all of these coordinates, and we have one more Plücker coordinate that is a coordinate on this ambient affine space. That is corresponding to the subset 2, 4. So we have all of these. Actually, I will put it on the second coordinate. And this is exactly the expression that I will use. Right? So here I have. Okay. And now if I tropicalize this map, so I send a tuple. I go from my initial torus, which translates now to just the lattice, to the tropicalization, or let's write down the fan to the tropicalization of the Plücker ideal. Like this. And now we can see what happens to our cones here. So sigma S was the cone where this term wins the race of the maximum. So if I map it over there and I consider points in the image, and let's call this one now U24. Or let's see if I take So if I have take W in the image of my cone sigma S, then this condition exactly ensures that W is in which of the cones? 1, 3, and 2, 4. The same. 1, 2, and 3, 4. Okay, so let's do the computation. So now we want to check where we land on this side. So we have to compute these values and see which conditions hold. And so W24 here, I can replace it by this expression, but I started in sigma S. So I know that the first term wins the race of the maximum. So I have, this is minus W, this is W13 minus W13 plus W12 plus W34. And then I have the cancellation. And I see that I land in the cone tau 14. Right, so let's write down tau 14. Let me check my notes to not mess this up. Right, so this is the condition of being in W14. If this sum is less than the other two, this corresponding to the weight of this term, I keep these two terms. And this is exactly the condition we have here. Right, so sigma S, the image of sigma S is the cone tau 14. And then similarly, we have, we can compute that the tropicalization of the image of sigma S prime is the cone 1, 2. Okay. And that is the statement of the theorem. Okay. Yeah. Yes, so absolutely. Better in the sense of positivity, right? So let's write down the equations that we would get here. This one has initial idea generated by, we already verified. We keep these two terms. Or maybe let me erase it like this. So this one has initial idea. I will write the tau 12 here. So these are the initial forms I get of my generator, and this one is not totally positive. So we see in the image exactly, we only see those cones that have totally positive initial ID. Okay. Great. Okay, yeah, that's it actually. That's it on tropicalization. So I will take a little pause and see if there's more questions coming up, or we go to cluster structures on partial flag varieties. These U24s are arbitrary points in, yeah, if we would go only to integer points, then these are G vectors of cluster monomial. But we're in the real vector space generated by those. Mm-hmm. Okay, so first of all, I have to admit that my title and my abstract and my notes were like overly ambitious, and I will definitely not get to where I wanted to get in detail that I wanted to give. But I stated this result, and I want to present another result to you that relates cluster structures between flag varieties and Grassmannians, because both of those turn out to be useful and have applications in scattering amplitudes. And in my lecture tomorrow, I would like to give you like a bit of an overview or a brief insight on what these applications are. So now I'm gonna stop talking about tropicalization and go to partial flag. Maybe this was the third point on my initial list. But thankfully, we had many lectures by Yevgeny talking about flag varieties. So you're already very familiar with the object. Let me just write down the notation. So for me, a partial flag variety will be indexed by a tuple of integers, d1, dk, n. They're increasing, strictly increasing. And this is exactly tuples of vector spaces, all vector subspaces of C to the n. And one contained in the other. Let me write it like this. Right, so this corresponds in Yevgeny's notation to the weight that is just the sum of those fundamental weights. And Yevgeny also showed how this is an orbit closure of acting with a certain subgroup of SLN on the highest weight vector corresponding to the representation with highest weight lambda. So unfortunately, my conventions are a bit different, but not very much. So in Yevgeny's notation, we would consider the flag variety as a quotient of SLN by a parabolic group from the right, and I will do it from the left and with the opposite parabolic group. But so for me, this is a quotient of SLN on the left by a parabolic group P minus, and I give an example of these groups in a second. And then for me, it's more convenient to think about a subgroup of upper triangular. So let's do an example. The flag 2, 4, 5. So I am in n is equal to 5. 2 and 4 are my support. Then this parabolic subgroup is of the following form. And the corresponding unipotent group, which is also denoted by U in the notes, but I will try to change to n now. Okay, so how can I see this inside the flag variety? Or like in particular, this means that I have a copy of the group sitting inside the flag variety and it's open and dense. And how do I get that? Well, if I take a matrix, I would just read off row-wise the generators for my vector spaces. So these two would generate a vector space V2. And these four would generate a vector space V4, and V2 sits in V4, and that's my point in the flag. Okay. Oops. So I mean, my convention also changes. I think in your convention here, you would take columns that generate the vector spaces, and I take rows. Yes. So yes. Oh, I think yeah. I think to transpose the matrix. Yeah. Yeah. So this convention follows Geisler-Clark. Okay. Right. Okay. So yes, I have a bit more time. I want to tell you how to get to an initial seed for the cluster algebra, that is the Plücker algebra of a partial flag variety. And this is a construction, still have space, of Geisler-Clark and Schrawan. And I will do this on an example. And if you want to know the details for other cases, you can check them. By the way, I'm updating the notes essentially every day because there are so many typos. So if you downloaded them, just refresh the page and download again. Okay, so here's what I'm going to do to get to an initial seed. And we will keep doing this in the example of the flag variety 2 for n equals 5. So first thing I do is I draw a pseudo-line arrangement of a permutation corresponding to this flag variety. So combinatorially is the following. I write down the numbers 1 to 5 in my x-axis, in my y-axis, and I mark the tuple of the support of my flag. And then I draw wires or pseudo lines in such a way that the ones of these blocks don't intersect. And I send the first block to the last many elements up here. So here I would connect 1 and 4 and 2 and 5, and then I continue. And I read a permutation from this by looking at the endpoints of my wires and have these indices be the images of the endpoint. Well, I could, yes, I could circle 5, but it wouldn't change anything because it always would just go to the 1. So the rule for the wires is that wires in these blocks don't intersect. And I'm sending the last block to the topmost element. Right, so, and then I can read off a permutation from this diagram by saying that the image of the endpoint of a wire is the starting point. So this would be sigma of 4, sigma of 5, sigma of 2, sigma of 3, and sigma of 1. And the permutation I get here is the permutation of the corresponding parabolic. So if I write down my sigma, this is 5, no, is it? Oh, yes. 3, 4, 1, 2. Okay, but I will not comment much more on these permutations. So this is my groundwork. From this diagram, I will now extract a quiver, and I will extract the initial cluster. So this is step 1. Draw a pseudo-line arrangement. And then step 2 is draw a quiver. And this quiver will have vertices corresponding to all the faces in my diagram that are either bounded or unbounded to the left. So vertices let's say mutable vertices, bounded faces, frozen vertices, unbounded faces, unbounded to the left. So I get mutable vertices like this, frozen vertices here. And then I have 2 extra frozen vertices that are not from the diagram that correspond to my support, to my indices in the support. Plus additional frozens. One for each DI. So in this case, I have 2, and I will place them here. So this one will be my D2 frozen vertex, and I have another D4 frozen vertex. No, here down here I don't have vertices. Which one? This one. Yes. No, so this one, yeah, okay. Or let's say unbounded only to the left. Yeah. Yes. So I don't consider the ones that are unbounded to the bottom. Only. Yeah, exactly. But the ones are just, yeah, definitely. Yeah, for sure. not the ones above. Yeah. Right. Right. So for the unipotent cell, you also add additional ones. And what are they? They are these spaces. So if you would have the full unipotent cell, then yeah, your pseudo-line arrangement is a bit bigger because you want the longest word to be the permutation associated to it. Okay, I think yeah, probably there's variations depending on what, yeah. Yeah, okay, yes, so sorry. You're right. Yeah, just the unipotent cell is not, you don't have these two. And what guys Leclerc showed me is they actually first they contract something for this unipotent cell, for these different unipotent cells associated to the parabolics, and then they lift the cluster structure, and in the lifting you get extra frozen. Okay, so just let me draw the arrows. And when between the faces, the arrows follow this rule that they go from top to bottom if two faces share an edge. Okay, I can ignore the ones between frozen. And they also go diagonally through nodes. Like this. And then I have to modify this rule a bit to say what are these. And I would give you the answer in this case, but there's also a combinatorial way to compute these. There, in this case, they're like this. Okay, so this is my quiver. And maybe I stop here and I will give you the construction of the cluster variable.
Thank you. Any questions?
Yes. Yes. Yeah. I mean, this is so the partial flag varieties include the Grassmannian, right? If we just have one support, and if I would do the construction for the Grassmannian, I get this rectangular initial sequence. I also have all the oriented three cycles. So there's a way to associate weights to the vertices, and you want the quiver to be balanced with respect to these weights. And the weights actually tell you about the degrees of the corresponding cluster variables in terms of the coordinates. And homogenizing the quiver so that it becomes balanced with respect to these weights is what gives you the rule to add. And I mean, in this case, it would, you can make it planar. Yeah, you can move this one here. So these vertices, they always occur where they come for every di. So I always have some crossing of this line corresponding to di with the next one, di plus 1. And I could place this d2 here, and then it would always be planar. So this is maybe the rule. If you don't want to think about weights or anything, you look at di, you look at the crossing with the next line, and you place a frozen vertex here and create an oriented three cycle. So in Geiss-Leclerc and Schroer, they cover tapes ADE. This construction is a bit a modification of what they give. And you have also cluster structures for arbitrary flag varieties. But I believe, I don't know if there are still combinatorial rules like this. Yeah, so I think what you, yeah, but Bernschiff, I think, is it this one? Yeah, yeah. So they construct diagrams, which are kind of generalizations of quivers for non-screw symmetric types. Yeah.
Any other questions before we break? Well, thank you very much, Lara.
Thank you.